Hi, in this lecture, we'll start by talking about the span of a set of vectors. Okay, so we mentioned it before, but now we'll analyze it. Okay, so let's start by considering vectors v1 through vn that live inside Rm. Okay, so each of these vectors has m many coordinates. Okay, so our starting question is going to be, when does the span of these vectors equal the whole set, Rm? So remember, the span is all the linear combinations of the vectors. Okay. When does that span fill out all of Rm? Okay, so we'll answer this question by working through an example. So start with R3, okay? And we'll start with one vector u in R3 that's non-zero, and we'll try to build up a spanning set for R3. See what happens. Okay, so this is our first vector u. Okay, so this is a three-dimensional space. Let's think about the span of just this one vector. So the span of one vector is all the scalar multiples of that vector. Okay, so we have u, and we multiply u by every real number. Okay, so the span of u looks like this. Okay, it's what? It's a line through the origin, right? Okay, so it's a one-dimensional space here. Okay, so let's try to, remember, we're trying to build a set that spans R3. So let's add another vector to our set of vectors and see if what happens when we take the span of both of those vectors. So we're going to add v to our set of vectors. And then there's going to be two possibilities for what the span of u and v are going to look like. So here's the first possibility, possibility 1. If v is dependent on u, then the span is unchanged. Okay, what would it mean for v to be dependent on u? It would mean that it's a linear combination of u. In other words, it's a multiple of u. It lies in the span of u, which is this, right? It's this line here. So v is in blue here, and it is in the span of u here. Okay, so since it's dependent on u, when we take all linear combinations of both of them, right, we'll just get back the same line. Okay, v in this situation isn't giving us any new vectors when we take the span. Okay, so that's disappointing, right? Still a one-dimensional span. The other possibility, when we add v to the set, is that v is independent of u. Okay, so this is the sort of good situation. The span now fills a two-dimensional plane through the origin. Okay, so if v is independent of u, so I'm going to draw v here, right, outside of the line, which is the span of u, okay, then v has a span of its own, which is another different line through the origin, okay, and if we take the span of u and v together, what we'll get is a two-dimensional plane. Okay, so it may not be the easiest to see from this diagram, but just imagine three-dimensional space. Okay, so a plane is, well, think of a flat sheet of paper. Okay, and then just imagine it extends in all directions. Okay, and imagine it goes through the origin. Okay, so the span is a plane through the origin. Okay, so it seems like independence is the key to adding more dimension to your span. You won't need to add independent vectors to your spanning set. Okay, so if we have this span here and we wanted to sort of upgrade to spanning all of R3, what we would want to do is add another independent vector. Okay, so let's assume we're in this situation here. Okay, that is, assume that u and v are independent. We chose this situation. Okay, now we're going to add another vector w to the set. Okay, and again, there are two possibilities for what the span of u, v, w are going to be. Okay. One possibility is that w is dependent on u and v. Okay, in other words, w is a linear combination of u and v. In other words, w is on this plane here, the span. Okay, then if you add a dependent vector, then the span is unchanged. Okay, the span of u, v, w will equal the span of just u and v. Okay, so if we want to span R3, what we have to do, of course, is add a w that is independent of u and v. Okay, so we want to add a w that is outside of the span. In other words, it doesn't lie in this plane. Okay, if that happens, we get u, v, and w as an independent set. Okay, and that span of u, v, w now fills the whole space, right? It fills a three-dimensional space. Okay, and since we're in R3, we can say that the span of those vectors is equal to R3. Okay, so the lesson is to upgrade our span, that is, to make it bigger, a higher dimension, we need to add independent vectors. Okay, so if we think about u, v, and w, it spans all of R3. Now, if I were to add another vector into there, this set, say an x, well, that new vector will have to be dependent on u, v, and w. Okay? Remember, a fact we stated before was that if you have more vectors than dimension, that set is automatically dependent. Okay, so in other words, there cannot be 4 vectors in R3 that are independent. Okay, so, well, if I throw another vector into here, I'm not going to get more dimension, but does that change it? No. Okay, if I were to throw another vector x into here, it would be dependent on u, v, and w, but it would still span R3, right? It can't ruin that, right? So, okay, so here's the sort of lesson from what we set up here. Okay, so if we consider a set of vectors v1 through vn in Rm, then the span is all of Rm if there is a set of m independent vectors among the set of vectors v1 through vn. Okay, so if the whole thing is independent and we get m independent vectors, that's great. But if there's a subset of these vectors that is independent and it's m-sized, so this fact summarizes what we learned above. Okay, so if we consider a set of vectors v1 through vn in Rm, okay, then the span of the vectors will equal the whole space Rm if among these vectors there's a set of m independent vectors. Okay, so the whole thing doesn't necessarily have to be independent. It's just that there needs to be a subset of these vectors of size m that is independent. Okay, that's the requirement. Okay. In other words, we need the rank of the matrix A to equal m, where A is formed by putting these vectors as columns. Okay. So this theorem links together a lot of the concepts we've talked about with the fact we just demonstrated up here. Okay, so this is the theorem. Suppose A is an m by n matrix. Then the following are logically equivalent. Okay, so that means that for my matrix A, okay, it either has all of these properties, A through E, or it has none of these properties. Okay, that's the format of the following are logically equivalent type theorem, and we'll be seeing more of these type theorems in the future. Okay, so what are all the things that could be true about A? Okay, so the first thing is that for each B in Rm, the equation Ax equals B has a solution. Okay. The second thing is that each B in Rm is a linear combination of the columns of A. So we know from talking about linear combinations and examining this equation that these two are the same thing, right? And also, part C, the columns of A span Rm. That's the same as this. That's the same as the one above it, right? So D and E introduce the new things we learned. Okay, so A has a pivot position in every row. Okay, so remember, our condition that we wanted here was that rank A equals m. Okay, so since A is an m by n matrix, m rows, what we're looking for in that condition is that each row has a pivot. Okay, and the last one, E, says that rank A equals m. Right? It has m many pivots. Okay, so when we have a theorem like this, and we want to know, are all these properties true for A? Right? We have some options on how to test it. Right? We can test it for any of these, but the easiest one is just to check its rank. Right? Check if it has a pivot in each row. That's the same as checking its rank to be n. Okay, so if we check this, then we automatically know that all these are also true. And if it turns out that the rank is less than m, then we know that all of these are false. So in part A of the theorem, it says that the equation Ax equals B has a solution. Okay, so if you remember from the previous lecture, we know that in solving for Ax equals B, there are three possibilities, right? No solutions, a unique solution, or infinitely many solutions. So here A is just saying that it has a solution. Okay, so that's opening the door to two possibilities, right? It could have infinitely many solutions or a unique solution. It's just saying there's at least one. Okay, so the next natural question is that if we suppose A is an m by n matrix, and suppose it has rank m, so all of these are true. Okay, so in particular, we know that Ax equals b has at least one solution for every b in Rm. So now we can ask, which case are we in? Are we in the case of a unique solution, or are we in the case of infinitely many solutions? Okay, and what property of A determines which case we're in? Okay, so we'll illustrate the answer to this question by looking at two examples here. Okay, so the first example is the matrix A1. Okay, so in A1, I'm going to have 3 vectors in R3. Okay, so it's going to be a 3 by 3 matrix. V1, V2, V3 are the columns. Okay, and I'm going to have the condition that it's an independent set. Okay, so that's the first example. The second example is I'm going to have 4 vectors in R3. Okay, so it's a 3 by 4 matrix. And we're going to have that the first 3 are independent, and the fourth is dependent on the first 3 in this way. Okay, so V4 can be written as just a combination, a direct combination of V1, V2, and V3. So that means that V1, V2, V3 is a dependent set. Okay, so if you remember a fact from a previous lecture, we stated that if the number of vectors exceeds the dimension of the space they're in, then they're automatically dependent. Okay, so any set of 4 vectors in R3 is going to be dependent. Okay, but the sort of point here is that the set is dependent overall, but we do have a subset of the vectors that's independent and of size 3, which is the dimension of the space. Okay, so we're going to ask, how many solutions does this matrix have for A1 x equals b, and how many solutions do we get here? Okay, so the rank of A1 is 3. It has 3 independent vectors. Okay, the rank of A2 is 3 because the largest set or subset of independent vectors in the set is 3. Okay, so by the previous theorem, both sets of column vectors span R3. Okay, so they have the same span. So let B be a vector in R3. And now we're going to try to solve for A1x equals b and A2x equals b, and see, do they have a different number of solutions? Okay, depending on if it's 3 independent vectors in R3 or if it's 4 dependent vectors, but with a subset of 3 independent vectors. Does that make a difference? Okay, and of course it does. Let's see. Remember, the strategy for solving such a set or such an equation is we write out the augmented matrix and then we put that into reduced echelon form. Okay, so for A1, this is what we get. We put it into reduced echelon form and we get 3 pivots as expected because it's 3 independent vectors. Okay, and so here we have a unique solution. Why? Because each column associated to a variable has a pivot in it, right? And there are no columns without pivots. that means we have a unique solution. And we can just read off what that unique solution is right from the reduced to echelon form here. Okay, so x1 is going to be c1, x2 is going to be c2, and x3 is going to be c3, whatever those numbers happen to be here. Okay, you can also write B as an explicit linear combination of v1 through v3 using these weights like this. Okay, so everything's simple and clean here. Okay, getting one unique solution. For the other example, okay, for A2, when we put this into reduced row echelon form, what will we get? Well, now remember the size of our matrix, A2 is a bigger matrix, so it has 4 columns. That means our X has 4 entries in it. So our variable, so we have 4 variables like this, right? Okay, so we put this into reduced row echelon form, and the first 3 columns are independent, so we get a pivot for each one of those. But X4, there's not enough room to give him a pivot. Okay, since V4 is dependent on the first 3 vectors, X4 is going to be a free variable here. Okay, and so we'll get infinitely many solutions. Okay, and we can write out what the general form of those solutions are going to be. Okay, and it'll look something like this. Okay. Remember, from row 1, we can isolate for x1, right? So it'd be c1 minus x4. Okay, and similarly for x2 and x3. And x4 is just a free variable, so it's just equal to itself here. Okay, and we can decompose the vector like this if we choose to. Okay, and here, since x4 is a free variable, x4 runs over all the real numbers. Okay, that's how we're getting infinitely many solutions here. And we can also write B as a linear combination of the V's, where these are the weights, right, coming from here. Okay, and again, we let x4 run over all the real numbers. Okay, so this is quite messy, and this is quite clean over here. Okay, so we can answer our question now. What are the conditions on A that will make the solution unique? Okay, from this we can see that the solution is unique when we have exactly m independent columns. Okay, so what we want is m independent columns and no more. Otherwise, we'll still be able to solve it, but it's much messier. Okay. Also note, in the situation where we have a unique solution, A is necessarily a square matrix, right? The vectors are in Rm, and we need exactly m of them. So it would be an m by m matrix in that case. Okay, so square matrices have nicer computational properties than non-square matrices. In particular, there are inverses of square matrices. Okay, so if I look at this matrix here, A1 times x equals b. Okay, what I could do to solve for b is compute the inverse of A1, okay, and then multiply both sides of this equation by the inverse of A1, and I'll have isolated for x, and I'd get this solution using that method. Okay, I can't use that method for this equation, a2x equals b. Why? Because a2 is a non-square matrix. And inverses aren't defined for non-square matrices. Okay, so that's another advantage to not having extra dependent columns or vectors. Okay, so what's the lesson of this? Okay, so the lesson is it's preferable to choose a spanning set of vectors to be minimal in size. Okay, that way you get unique solutions like this. Okay, and when we have a minimal spanning set for a space, okay, it's called a basis for that space. Okay, so we'll talk a lot more about basis and bases later. Okay, and we'll state this fact because it's useful to remember. Okay, really this is a consequence of this theorem and this fact. Any set of m many independent vectors in Rm will span Rm. Okay, and such a set will also automatically be a basis for Rm. Okay, like I said, we'll carefully define what basis is later, but you can think of it as the most efficient way to span a set. No additional redundant vectors in there. Okay. So now I want to talk about a special case of the equation ax equals b, okay, called a homogeneous system. Okay. So this is the definition. So if I have ax equals b, and I set b equal to the 0 vector, then ax equals 0 is called a homogeneous equation. Okay, so we can ask, how many solutions does ax equals 0 have? Okay, so first of all, note that we always have the trivial solution to this equation, right? If I just set x equal to 0, then a times the 0 vector is going to equal to 0 vector, right? No matter what a is. Okay, so always know there's at least one solution. Okay, so now let's make the following observation, which will connect ax equals 0 to linear independence. Okay, so let v1 through vq be columns of A, and observe that if we write out the equation ax equals the 0 vector, it is the dependence equation of v1 through vq, the vectors. Okay, so remember, when we're talking about linear independence, we had this starred dependence equation which we studied. Okay, and it looked exactly like this, right? If this equation had only the trivial solution, that is, only when the x's are all 0, this is true, then the vectors were independent. Okay, and if there were some other solution, then they were dependent. Okay, so a times x, right, when you multiply it out, is equal to this, right? Just using the linear combination of columns method, right? Okay, so solving for the homogeneous system is equivalent to determining if the vectors, the column vectors, are dependent or not. Okay, what we're asking about, what could the weights, what could the x's be possibly? Okay, so here's this theorem that categorizes this. Okay, so consider the homogeneous equation, ax equals the zero vector. There are two possibilities, okay? So one possibility is that we only have the trivial solution, okay? The only solution to this is that all the x's equals 0. And of course, that goes along with the columns being independent, just by definition of linear independence, if we only have the trivial solution. Okay. Other possibility is that there are some non-trivial solutions to this equation. Okay. And that implies that the columns are dependent.